third Agda stream, I guess. And we're gonna do chapter 3 of Programming Language Foundations in Agda. Oh, I should clone a project. I haven't done it yet. But yeah, so we did the first 2 chapters already. On my own time, I finished the exercises from chapter 2, and we'll actually step through that before diving into chapter 3, because I want to show off what I made. I'm kind of proud of it, even though I didn't do that. Well, you know, they're brutes. Like they don't even execute, you know. But yeah, I am proud of it. Let me see. I'll first say Discord streaming now. Let's clone the GitHub project. So I don't know if I can find it. I should have access to GitHub. And then I did things to Agda. I don't know where it is. I have to log in. Oh right. Okay. So I probably should do that off stream. Yeah, you can watch the car. Come on, I3, you can do this. Sign up. Sign in. Oh, it's laggy. Come on, computer. Keep up with the flow. Yeah, I can open up my password manager and then log into GitHub to show how far I am with that. Actually, I need the project anyway because it has the unique shell for Agda. Fortunately for me, everything is reproducible, so it should be quite easy to set up the Agda stuff again. Even though you can see how ill prepared my stream is, like always. I didn't expect Agda to not be there, but then I realized that the last time I streamed Agda is like a month ago, because, you know, meanwhile I have been doing all the exercises, and I did a planner stream as well, which is like Haskell, you know. So yeah, we haven't done Agda in a while, so it's good to get back into it. You know, 1 extra Agda stream a month to keep us busy with it. We slowly go through the book. I had this idea in my mind that doing the exercise on stream wouldn't be good content, because I was afraid that I would get stuck a long time on something I could just not figure out, which actually happened in the first part of the induction chapter. So I got really stuck on I think we can talk about it when I go through the exercises. So before we talk about the last chapter and how I did there, let me first clone the project. I can figure out where my credentials are. I already opened the password manager, which is good for me, because normally it takes ages for me to open the password manager, because I always type my password wrong because I made it too long. Yeah, too scary. And so now I need to do 2-factor authentication. It really wants to know that I have my phone. Actually, something I've been thinking about is setting up an Nbox just to do all the 2-factor authentication shit. So my 2-factor authentication is no longer 2-factor authentication, because I just, you know, put it in a Nbox ISO, and then put the Nbox thing in sync thing. So it's all on my PC basically. That's just things. That's my usual, you know, degeneracy, I suppose, trying to get around 2-factor authentication. This would work as well, I think, because the Authenticator app doesn't really, you know, give a shit where it's being executed from. It doesn't have to be an Android device. Although I guess technically an Nbox is an Android device. But yeah, so PLFA. I can open it up now and you can see I have PLFA. So some guy asked me to do, well, he may be viewing right now, I don't know. But yeah, some person asked me to not publicize the exercises. And I thought about it for a while. I was first, you know, my default policy is to make everything public, but I was also, the reason he didn't want that is because these exercises are used in classes. And I thought like, yeah, it would be kind of annoying if I would be a teacher and someone would upload the answers to exercises, because, you know, you have to keep on rehashing them. It's annoying. So I decided to make them private. So we can still stream them, I think. Like, you know, if someone wants to go through hours of my beautifully crafted videos instead of actually learning something, then, oh, good for me, I guess. But I doubt anyone will do that. Still, it would be also really annoying to type over from video. Like, I think you would have a lot more fun just doing the Agda. But yeah, that's I'll make it at least so difficult they have to watch my videos. That's my contribution to Agda. Yeah, I copied it, but Emacs doesn't update. So yeah, it's here now. I actually don't know if we actually using the Nix stuff, but well, anyway, here it is. No, I don't think we're using it at all, to be honest. We just Ctrl-C, Ctrl-L, and then Emacs figures it out, right? Yes, Emacs figures it out. So we did even the stretch exercises. That's no, not all of them. I didn't do the binary ones because I was annoyed. Like I remember doing a poorly implementation. I was like, okay, it's good enough. Like I know how induction works at this point. We don't have to do it anymore. And I'll show you because yeah, I did them all basically. Well, except the binary one. I was properly annoyed by this one, you know, because it gets repetitive. It's always the same trick, the same little bag of tricks. They really jam it home at you. But I got really stuck on this one because star distrib plus. I got stuck because I needed suck R, I think. Oh, that's the other one. That's community. No, I couldn't figure out suck. So I couldn't figure out how to make the definition become a rule. We made this definition suck for times, right? We did it in naturals. This was the first stream. So we have a definition for well, multiplication basically. And as you can see, the definition for multiplication is very similar to this law. So it's this one. It's suck m times n is equal to n plus m times n. So that's suck m times n is equal to n plus m times n. If you have a situation where these are the same, you use REFL. That's what REFL does. It says like, okay, you just do one of these. We don't say which one, but just figure it out, you know, REFL. Go to the definition. That's what it's saying. So we can use that for the, let me think, we can do that for the, this case as well. If the, if you got a 0 times an n is equal to 0, which is this one, right? 0 times n is equal to 0, then you can do REFL. I think we can do this entire thing as REFL. If we just put an m in here. Yes, that's pretty. That's one of the things that surprised me about Agda as well, is that you can, at times, wait, maybe we can do this one as well. No, that's not complete now. You can make pretty things, like you can delete definitions. I think I noticed this in the first stream as well, but yeah. So we just deleted one rule here and it just worked. It's great. Yeah, we can see that in the git diff. I was just thinking like, I was on the wrong line here. We deleted it for eliminate L. And I realized that these names are not correct either. Like this, I think this is supposed to be identity. Maybe not, I don't know. No, I don't think it's an entity. Yeah, I call it eliminate. I don't think it's supposed to be called eliminate, but you know, that's my math knowledge. So I just gave it some name. I'm calling it eliminate because you go to 0 and you can always attach an m to it. I think in logic we would call it weakening. Yeah, we call this weakening because you have this definition which is strong and then you add like an m to it because it doesn't do anything. So you make the definition weaker. You can make it more strong or whatever. So yeah, we deleted this line because we looked at the definitions and we realized that it's just REFL. If we replace this with an M, it's, yeah. But that's pretty cool. Delete superfluous line. Okay, do I want to step through all of the... I want to step through suck R. Suck R was so annoying. I needed this one. I needed this n times suck M is equal to n plus... So this is like slightly reordered one of... this, like you can see it's flipped, and you may ask yourself why in the world would you ever need that? Well, to prove distributively. So we don't use it in a base case because we can use we can use other things in the base case because it's 0, so things become easier. But here we need suck R, and I don't know if suck R is the right. Wait, what? Oh, I was in the wrong. It's not in distribute. It's in commute. Of course, it's in commute. Yeah, so in the base case, we don't have to use suck R, but we have to use suck R here because, you know, we're stuck here with this thing. So we just conjugated that, and then we ended up with this situation. It's like, okay, how do you continue from this situation? Well, you use the symmetry of suck R, actually. So yeah, you can't use normal suck. You use suck R. What does suck stand for? I don't know. I just made up these names. So what I do is basically look at the type signatures a lot. So, and then I just like kind of try to figure out what I need and go from there. I don't know if this makes sense. At some point you end up with raffle, and then it's, you know, definition. It's a simple case. I was happy with raffle, but yeah, this one was really nasty. It took me a while. I think it took me because at that point I already knew the raffle trick, but still to go through this proof took me like at least 3 hours, I think. So yeah, it takes a long time. Okay, so I think we're done reviewing this chapter. Is there anything else interesting? Yeah, and after this one was definitely the most difficult, and after that it just kind of became easier. I don't know, maybe the proofs still got bigger, but I kind of knew how it all worked at this point. And oh, some of these are really... Alright, the multiplication was really... no, it was also not that. I think bonus was kind of difficult for different reasons. I don't know. Yeah, just like getting the right combinators can be challenging. Because you don't know, in the beginning you don't know which one you need, so you just start adding obvious rules and then hope you have enough building blocks to figure it out, right? So, you know, you work a little bit on this proof, and then like, oh, I need some other building block. You go back and you think, and then add another one. But some of these didn't work out. So I tried adding rules that don't make any sense at all. That was fun for Modus. Monus. I don't remember what I wanted to do, but yeah. I remember struggling with that a little bit. And then I just thought more and figured it out. Okay. Let's move on to the next chapter. I guess I reserved reading the chapter for stream, which is, you know, always exciting. Yeah, let's go on to relations, inductive definitions of relations. After having defined operations such as addition and multiplication, the next step is to define relation, such as less than or equal. Okay. The relation less than or equal has an infinite number of instances. Here are a few of them. So, okay. And yet we can't write a finite definition that encompasses these integers if you like. Here is a subpar of inference rules. So, let's see. 0 is the smallest of the naturals. So it's like your base case. And then, what? If m is smaller than n, then successor of m is also smaller than successor of n. Oh, you wrote it as data. Okay. That's something I sometimes, like, I'm still kind of wondering about, like, when do you use data and when do you use function? Here, that smaller than n, and are the constructions of names. Well, 0 is smaller than m and m is smaller than n. This occurs first index data type. Could you jam this into? This is our first use of an index data type, where the type m is smaller than n is indexed by two naturals, m and n. In Agda, a line beginning with 2 or more dashes is a comment, and we have exploited that convention to write Agda in the form of the ref samples or corresponding inference rules. A trick we'll use often from now on. I would say the definition is like already so close to it. Well, I guess you could use the trick. Let's actually make a new module and copy over this stuff. I think we're gonna need it. So yeah, let's copy it over. And we'll call this. Let's see. Which one is it? Oh, this one. So we need to call this relations. Agda. Okay. Relations. We'll rip it out. Copy over this stuff. Copy over the indexed data things. Not sure what I meant by that, but I guess we just kind of plow on. I don't know. Yeah, time for a quick water break. I ate too much. I guess. Oh, I didn't announce here as well. What the? Let's do that. Okay, cool. And then when I announce, I'm gonna just open up the water break screen. Quick fika break, because I need to get some water. So be right back. Okay, I'm back. I got water. Good. Yeah, let's go back into Agda mode. In Agda, any line beginning with yeah, that's a comment. Okay, both definitions will tell us two things. Based in this case, in fact, they'll give a bit more. They'll give us each a bit more detail. Base case for all naturals, and the constructor produces evidence that 0 equals to n hold. What? So if you use that constructor, which I presume which you can pattern match upon, you have the n is bigger than 0, I guess, or equal to 0. You're not really saying anything about n, to be honest, with the base case. Because it's a natural. It's like, oh, you're bigger than what? You just say nothing about it. Okay, cool. And you have the other case. How you gonna read that? S equal or smaller than s. Suck. Oh right. You gotta suck. You gotta suck m and you gotta suck n. And m is equal or smaller than n. You put in an m equal to smaller than n, and if you put on both sides +1, the relation is still the same. Okay. I mean, again, I feel you're not really saying a lot, but it's me, man. Like, you know, we'll just yeah, for examples, you can put in the examples, and you know that this doesn't tell you much, and yeah, if you put in 1, 3, and then you 2, 4, it's the same thing, right? Increase on both sides, and the relation would be the same. I guess that's what you're saying about the relation. That's okay. So you have this relation, and you know that everything is bigger than bigger or equal to 0 because it's a natural. So we know that thing. And another thing we know is that if you have a number here and a number there, you can increase them on both sides and nothing will change. So okay, that's what we're saying. It's like okay, very precise. This is our first use of implicit arguments. In the definition, if what? Implicit? What? No. Why? This is our first use of implicit arguments. In the definition of inequality, the two lines defining the constructor for all. Two lines defining the constructor use for all. Very similar to our use of for all in propositions such as. It's very similar. Is that like missing a word? Maybe? Oh. However, here the declarations are surrounded by curly braces rather than parentheses. This means that the arguments are implicit. Wait, where do you see it surrounded by? Oh, in here! Implicit. Or the declarations are curly braces rather than parentheses. This means the arguments are implicit and need not to be written explicitly. Instead, they are inferred by Agda's type checker. Scala time! Scala. This we write com for the proof n plus n, but we write for the proof 0, leaving n implicit. Similarly, if evidence that we write if m equals smaller than n is evidence that m is equal to smaller than n, we write for evidence you don't need to put in the m's and n's. Okay, cool. So how does it not like, you know, mix? Because they're like 2. So how does it know not to, you know, maybe it doesn't matter or something? I don't know. It's like pointwise by default. It doesn't tell you, does it? If we wish, it is possible to provide arguments explicitly by writing the arguments in curly braces. You're gonna make it more difficult, okay? Here in Agda, it proved that 2 is repeated with implicit arguments made explicit. One may also identify implicit arguments by name. 2 is equal to 4, 1, 3. Or maybe it can do a single step or something, who knows. One may also identify implicit arguments by name. In the latter format, you can choose to only supply some implicit arguments. Okay, that kind of makes sense. You kind of end up doing this stuff in Haskell a lot because you don't actually, like, having many positional arguments is difficult after a while. Like, you have more than 4 or 5, it becomes really confusing. So yeah, just doing name based isn't too bad, I suppose. Okay, in a latter format you can choose only to supply implicit arguments. It is not permitted to swap implicit arguments, even when named. Oh, well, that sucks. What? We can ask Agda the same inference by writing underscore, for example. We can define a variant of the proposition identity with implicit arguments. We use ask Agda to infer the value explicit argument from context. Try to invert an explicit term. Oh, that's pretty cool. There's only one value which gives us the explicit proof, so Agda happily fills this. If Agda fails to infer the value, it reports an error. You can always try to put in that, and it will just sometimes work. We declare precedence for comparison as follows. We declare precedence for comparison we set the precedence of smaller n at level 4. Spline is less tightly than plus. At level 6 and hence, we write infix to indicate where an operation does not associate to either left or right. It makes it no sense to parse it as. Given two numbers, it's straightforward to compute whether or not the first is less than or equal to the second. We don't give code for doing so here, but we'll run straightforward to compute whether or not the first is less or equal to the second. We don't give the code doing so here, but we'll return on this potent job decidable inversion. In our second definition, we go from smaller things to larger things. For instance, m equal to smaller than n. We can conclude suc where suc m is bigger than m. Suc n is bigger than n. But sometimes we want to go from bigger things to smaller things. There's one way to prove that suc m. Let us invert our previous rule. Yeah, but this is just like a normal pattern match, right? Here, with two spaces. You're just stripping it out with a pattern match. Okay, this is in here. It's the constructor, so you can just fill it out. I mean, I'm assuming you can just do this, right? What? What did I do? Wait. Give me a moment. You're putting in a suc m and a suc n. And you're supposed to return an m is smaller than n. Keep in mind, this is just a constructor. This is the constructor of the type equals, but this is like a pack. So we are simply pattern matching on this because it's a gathered. So in Haskell we would represent this as hello Barry Bluent, how are you? Welcome to my epic Agda stream, where we slowly but surely are going through this book. Yeah, so this is a gathered. So the way to look at this is a field in the record. So this thing has no fields. Yeah, this has no fields. It's just 0. But this thing has one field, and we're just simply pattern matching on that and getting it out. So that's the magic. It is like a gathered in Haskell. Exactly. You are right. I think even they stole the syntax from Agda, but I'm not sure about that. So yeah, we inverted the rule. Yeah, I'm still having trouble parsing this, but I get what's going on. I'm just having trouble to believe it, I guess. I mean, if I walk through it step by step, I understand what's going on, but I'm just having trouble. I don't know what, just not accepting reality or something. It's a variable name, while m is smaller than n is a type. The latter is a type of the former. It is a common convention for Agda to derive the variable name by removing the spaces from the type. Not every rule is invertible. Indeed, our rule for Zn has no, because like, there's nothing to pattern match upon. So yeah, well, we can pattern match on something, but like, when you give back 0, it's not gonna change anything. Indeed, our rule has no implicit hypothesis, so there's nothing to invert. Like I said, there's nothing to pattern match upon. Because, well, they say it's the hypothesis, but if we go all the way back to natural, we can see that these things are the same. So yeah, because judgment conclusion. Okay, we don't know what the hypothesis is. I'm sorry. Hypothesis. Each inference consists of 0 or more judgments written above a horizontal line, called the hypothesis. Okay, there we go. So yeah, the stuff we put in here is the hypothesis because it's above the line. But in here, there's nothing above the line except types, and that doesn't count. So yeah. Okay, cool. Another example of the inversion is showing that there's only one way a number can be less than or equal to 0. Did you just? So they wrote out raffle. You know, I like to call it a fixed point, but I suppose you could also say that. Let's copy paste. You're probably gonna need it for proofs later. So, good copy paste monad, citizens. Okay, properties of ordering relations. Relations pop up all the time. No, there you go. And mathematicians have agreed on names for some of the most common properties. Reflexive for all n, the relation n. Reflexive. N is equal smaller than n for all n. Smaller than n. How can you be smaller than n? You're n. Makes sense to me. Oh, I suppose. Okay. Transitive. For all m and n and p, if m is equal and smaller than n, and n is equal to smaller than p, then m is equal to smaller than. So it's like a triangle. It's got like the m, the n, and the p. One triangle corner, two triangle corner, three triangle corner. And then you get like, oh, one corner is like that, and then the other corner is like that. Okay, let's connect up the m, which is here, and the n is there, and the n is there, and then you know you can skip the entire n comparison. So you can go straight to p. You can compare m to n, and you can compare n to p. Then you can also compare m to p. Oh my god. Antisymmetric, symmetric, antisymmetric, symmetric. Symmetric, antisymmetric. For all m and n, if both m is equal or smaller than n, and n is equal or smaller than n, hold then m must be equal to n. Total for all m and n, either m is equal to small n or n is equal to small n. So one is smaller than the other. That's total. Okay, like we just got a bunch of maths, I guess. The relation satisfies all of what? So here is a bunch of properties. We just express these properties in the relations you just defined. Oh, by the way, this relation satisfies all of these properties. So what are the properties then? A joke. Okay, so yeah, you know, just when I thought I kind of understood what this was, I've seen this in logic as well. So these are like a thing on their own. I guess you can also swap out the relation, like the operator in here. Like maybe you can use it for plus or whatever, and it wouldn't work. You could say they hold the properties on. Like you could say that plus is not reflexive because if you put n in n plus n, yeah, it's not the same anymore, right? So yeah. Yeah, 0 plus 0, I guess, is reflexive, whatever. So yeah, just if you just talk about 0, then it's reflexive for plus, but not for all n. Unless you define the set of size, well, 1, it's only 0 in it, then yeah, okay, whatever. Let's continue. Pre-order, any relation that is reflexive and transitive. Partial order, any pre-order that is also antisymmetric. Symmetric. Total order, any partial order that is also total. Okay. If you ever bump into a relation at a party, you know how to make small talk by asking it whether it is reflexive, transitive, antisymmetric, and total. Or instead you may ask whether it's... Yes, that's what I will do at a party when I encounter something like that at a party. Are they just joking that maths is not real or something? Is this what this is? Less frivolously, if you ever bump into a relation while reading a technical paper. Okay. Exercise ordering. Give an example of a pre-order that is not a partial order. Any relation that is reflexive and transitive. Sophia. Oh no. What? Pre-order that is not a partial order. Give an example of a partial order that is not a total order. Okay. An example of a pre-order that is not a partial order. Partial order. Partial order is a pre-order that is also antisymmetric. Symmetric? So give an example of a pre-order that is this like minus something? I don't know. 4 minus 4. I have no idea. I'll ask Sophia about this actually off stream because I have no idea. Yeah. Yeah, I'm gonna skip this question because I'm too dumb. I'm sorry. But happy there are now 5 viewers. I can see me being dumb. But such is life, you know? At least they can appreciate my smooth brain. I'm gonna put it in here so I don't forget to ask. Okay, cool. I'll be back on this at some later date and I'll have the answer. But for now, we're just gonna skip it. Because I came here for Agda and not clever math things. I guess like maths would hopefully be a side effect. Yeah, I'm still not quite sure what a relation is, to be honest. I guess smaller than would like be all these three, because E smaller than would not be M, N, and M, right? So that's, but maybe it would be total. So what is total again? For all M and N, if both M smaller than or equal to N. I guess this is smaller than, actually. Oh, we solved it. So give an example of pre-order that's not a partial order. That's smaller than. Okay, cool. Do we have comments? There we go. We just guessed. We just put in something and then it works. Okay, so I guess we figured out that this is a relation. But why is minus and plus not a relation? Maybe because it not evaluates to truth. It evaluates to a number, so therefore it's not a relation. I don't know. By the way, horizontal lines in type signatures are just comments. Yes, you are right. Give an example of partial order that's not total order. Well, what is anti-symmetric? Because for total order, any partial order is also total. Any partial order that is also anti-symmetric. So it's these three, right? So that's a partial order. But you don't have the total ordering. So equality. M is equal to n equal to m. No, that's not right. Anti-symmetric. I don't know this one. Okay, I'll come. I think I did one. I think this one is correct, but I don't know on the top of my head how to give a partial order. It's not a total order because I have a hard time distinguishing these two. M is equal to smaller than n is equal to smaller than n, m is equal to n. For all m, either. Wait, this is weakening. What? Or n is equal to anti-symmetric. Any period is also anti-symmetric. Any partial order is also total. But that doesn't seem right because this is really strong, right? For all m and n, if both of these hold, then this holds. Oh. Give an example. Not a total order. I don't know. Oh no. Welcome, people, to my Agda stream. Yeah. How are y'all doing? What were y'all doing in your stream? I wonder. What made you come here? The first property to prove about comparison is that it's reflective. For any real number n, are you doing it in Haskell? We're doing Agda. Wait, did I say? Oh, I have the wrong title. I'm not doing Haskell at all. Agda. Agda PLFA. Part 3 relations. Sorry, you rated the wrong person. I tricked you with Haskell promises, and it's only Agda. And I'm not gonna change it either. And welcome everyone. These yuppie things. Haskell is for real, man. No, we're not doing Haskell, we're doing Agda. I'm not gonna do. This is Agda. We're just like writing little proofs. We're not even doing programming, to be honest. This is just I tricked you all. I'm sorry. I mean, it kind of looks like I got it, if you know what it is. So we have a pattern match here. It's almost like, you know, it's proofs. This is not real programming. The first property we prove about comparison is that it's reflexive. For any natural n, the relation n is equal to smaller than n holds. We will follow the convention by the standard library. But Stellar Clown, what were you doing on your stream? And what made you come here? I wonder. Anyway, I'll continue with the book. We follow the convention in the standard library and makes you make the argument implicit, as it will make it easier to prove reflexivity. So I guess we're just gonna copy paste Monad here, and because like we're going to end up needing these proofs later in the exercises. So yeah, the proof is straightforward. Well, it's raffle, right? So you need a pattern match like this as well. Okay. Wait, there's another raffle. Oh, you are the raffle. Oh, that's cool. Anyway, in the inductive case, the inductive case hypothesis gives us a proof, and applying s is smaller than s to yields a proof suck right. So that's raffle. It's a good exercise to prove reflex interactively in Emacs using holes and okay. Yeah, let's not. I don't know. I don't really like the whole system as the well, maybe I should. I don't know. It's a bit too much magic for me right now. I feel I'm just learning the language and it asks me to already do holes and stuff. I don't even know where to start, to be honest. Would you put like holes in here and there? I think it's like a split. Ctrl C. Please put the cursor on a goal. I don't even know what it is. Let's do that. It's yeah. So it's like maybe we should look it up how it works. It's like it uses the type system to figure out what to do, basically. So it's like code generation, except you know how they have like GitHub Autopilot. What this thing does, it's instead of using machine learning to figure that shit out. It's using the type system to figure out what should come into places. So you just like, you know, bash a bunch of buttons and suddenly your code will be written for you. Well, code, it's not really code, it's proof. You know, codes are proofs, proofs are code. For now, I'm gonna skip that exercise as well because there is no exercise marking. Therefore, it's not a real exercise. Try this. Try this. Oh, I need to do a question mark. X will be a hole. Oh. Risk commands put the cursor on a hole. Oh, Control C, Control L. That's it. I don't know why I pressed that, but it worked. I think this is a hole now. You lied to me. Control C, Control comma X. I guess. I don't know. I don't know what it could be. Empty for split on result X. There we go. Okay. And then so I put in the thing it should pattern match on or something. And then we can continue with 1. Maybe I need to put a cursor on the goal. Wait. Do it. Maybe 0. Control C, Control C. I don't know. Pattern match for the case. X. I don't know. Comma? Oh yeah. Do the goal. I don't know how to execute a goal. So yeah, I'm kind of new to Agda. Let's stick on space. No, that's not it. Yeah, so anyway, Amy told me that you can't use this in cubicle Agda anyway, so I don't know if it's worth to spend a lot of time on. Because, like, you know, my eventual goal is to do the cubicle Agda stuff and to help with the one lab, right? So yeah. Sorry, Agda people. I know it's a really cool idea. It's just not for me right now. I'm not that comfortable with Emacs bindings anyway. I use it in Vim style, like a noob. So sorry. Okay, transitivity. Second property we will approve about the transitivity for any naturals M and P if M hold, P hold. Yeah, we discussed this at length, and we can Control C, Control L to type check it. Here proof by induction is evident that M is smaller than N. In the base case, the first inequality holds by Z is equal to smaller than N. Is this one? Or actually proving that by. Oh, that's actually kind of cool. So what we're doing is we are that's actually, I want to show that. So here they use so many words to describe their properties. Here, transitive. So you can see they're putting in the M is equal to smaller than N here as like an argument to the function, and then they're putting the same in here, and then the result will be here, right? So this is the entire description of the relationship, and you attach types to it here. So we have the entire definition of transitivity in types, and then we prove it by pattern matching. So this relation gets proven simply by pattern matching, and I think that's cool. Yeah. So at least, like, you know, if you put spell maths like this out for me, I understand it. Well, I understand it now after you know, I guess a week of struggling with Agda. I now understand it. Antisymmetry, transitivity. Yeah. Okay, that's cool. In case the fact that N is equal to smaller than P is irrelevant, and we write underscore as a pattern match to indicate the corresponding evidence is unused. Right here, because you can use referral in a constructor, I guess. It's in 0 case, right? They're the same. Describing all the code, the inductive hypothesis establishes that M use the following goal. It just recurs into it. Okay, cool. Use pattern matching and recurs into it. Okay, I'm gonna go for another water break because all this talking makes me really thirsty. I'll be right back. You can watch the beautiful Arctic background or something. I don't know. I'll be right back. Not sure about this book. You know, when I'm reading all this text, it looks like it's going so slow. But when I do the exercises, they usually tend to be quite difficult. So I don't know what's going on with this, you know. Maybe we should just jump straight into the exercises and see if we get stuck at all. And then start reading. Wait, did they modify it or something? We could make the implicit parameters explicit. I'm not do that, that's too much. One might argue that this is clear, or one might argue that extra length obscures the essence of the proof. We will usually up for shorter proofs. So, okay. So I wonder what the authors are thinking about implicits, you know. Anyway, the technique of induction on evidence of property holds. Induction on evidence that am I the one reading so poorly, or is the text just a bit difficult? The technique of induction on evidence that a property holds. No, it's the text. Inducting on evidence that, rather than inductional values of which property holds, will turn out to be immensely valuable. That's not me, right? That's the book has difficult grammar, and one of we use often. Okay, so I read the sentence just now, but I haven't parsed, like, I understood it. So, technique on induction on evidence that the property holds will turn out to be immensely valuable. We can just cut out all this stuff. Technique of induction on evidence that the property. We already used it before, right? Symmetry. Yeah. I feel this is just like an extension of induction chapter at this point, but maybe. Oh, we have an exercise. Okay. This is where they separate the children from the grown-ups. This is where they separate the cis people from the femboys. Naturally, we are femboys, of course. So, well, in spirit at least. Again, the proof is induction over evidence. M is equal to small m. In this case, both inequalities hold by z is equal to smaller than n, and we are given the 0 right by Raffle. Show 0 is equal to 0 follows from reflexivity of equality, that is not reflexivity of inequality. What? In the inductive case, the first inequality holds, and the second inequality holds by I don't know what this is actually. S is equal to smaller than S. Who's successor? We are given. Maybe just look at the code instead of reading the text. Like, the text is so difficult to read. Maybe they did it on purpose. Just look at the code, boys. You can figure it out like that. Just look at the code, people. Right. So what do we have here? Antisymmetry. So we need to prove that if you get an m smaller than m and n smaller than m, we can assert that m is equal to n. So if they're both the same, if they're both 0, then you can use reproductivity. And if they both have successors on both sides, a better match on them and conjugate into it. I understand this because we have the type which wraps the sucks around it, right? So we're doing here, getting the essence out of it, getting the sucks out of them, because they already have sucks here. We're getting them out, and we're putting it again into this function, but we're ignoring the suck part with conj. So yeah, I know what conj does now. So this is actually we can write it out. 2, so it's x to suck x. Does it make sense? So we are ignoring the suck part of the expression, the type, and we're just focusing on this part. Suck. Look at that part. Read the text to explain. Like an entire suck around it. Back then. The above proof omits cases where one argument is an argument. Why is it okay to omit them? Well, if 1 is 0, can't even happen, right? Because if this is 0, then this becomes 0. So what is m supposed to be? Because it has to be smaller or equal to 0. So it has to be 0 here as well, and it has to be 0 here as well. Because this is 0, that becomes 0. But, like, that's impossible, right? That's a good question, actually. So, if n is 0, and m must be 0 too, because of the definition. I don't know how you would prove this, but I can write it like this, and that's my proof. Total. The fourth property to prove about comparison is that it's total. For all naturals m and n, either m is equal to smaller than n, or n is equal to smaller than m, or if both m and n are equal. It specifies totality p. Why are we using a function now? Totality. I don't get this. Evidence that total holds either forward where M is N are evidence that M and N respectively. For those familiar with logic, the above definition could be written as disjunction. Disjunction would be right. Hello, welcome. What's this wild new world? Yes, it's that you know, first day of the month again, where the moon is full, I'm full of energy, and I'll do a stream. How your Agda stage going? So actually, I finished most of the these proofs from induction. So I proved all of these because we just hit a wall of things to prove. And I think on stream I got stuck on one of them, but I even finished these, all of these. I have proofs of my proofs. So I know how to. I know like it's it's 300 lines long, this file. So yeah, we got like yeah. So exactly, I know how to induct. I guess I'm a really good inductor at this point in my life. And now we're moving on to the next part, which is relations. And in the beginning it looked easy, and it's in true Agda fashion, it's ramping up quite quickly throughout the chat. And I assume there will be many exercises, which we won't finish all, but monoticity total. So this is the one we got for free as well. And I suppose that monoticity will be the first one we have to actually think. Right. We'll do stretch as well. But I don't, I want to set some expectations. We're not going to finish this chapter today because I found out that these exercises may actually take a long time. And to try and jam them in 3 hours is not reasonable. Even sure I want to stream 3 hours, but well, I probably want to. I always want to, like, if I'm starting to stream, I want to do a big one. I don't want to do like a half stream. The fourth property proof about comparison is that it's total for any naturals M and N, either M or N or both, if M and N are equal. Evidence that total holds is either from difference forward or flipped. Oh, I get it. Okay, so either M is equal to smaller than N, or N is equal to smaller. So it's disjunction. Okay, got it. That's what I'm saying here. One of these two, or both. One of these two. So these. This is the encoding of these in Haskell. You got one or the other. So this is not even right? Because well, is it? Maybe it's right. In Haskell, you would use data these to encode total, because you can have left, you can have right, you can have a tuple of both of them. So I think they call it this, that, and those in the Haskell package. But we're not doing Haskell right now, so I'm not opening it. Haha. This is our first issue with a data type with parameters. In the case M and M, it is equivalent to the following index data type. There are more data types. What? I thought what is total prime? No. Each parameter of the type translates an implicit parameter of each constructor. Why is there a total prime? Wait. In this case, M and N is equivalent to the following index data type. Oh, you're distributing. Okay, I see. So you're explaining what this is. I suppose, because you're saying it's the same as putting the annotation here and here. But I'm not sure if that's right, because in Haskell, if you would say this, if you add the type to the instance had, it means something else, right? Actually, come to think of it, maybe this entirely functions different than in Haskell, because this will be an existential in Haskell. You need to put the type annotation in the top in Haskell to make it not existential. I haven't seen existential in Agda yet, so how dare you? How dare I? Yes. What did I do? This is equivalent to the following, so it's just syntactic sugar for them. So we don't know the existential syntax in Agda yet, if they have it at all, because existential is fucking annoying. So if you want to live in peace, don't use existentials. But each parameter of the type translates to implicit parameter of each constructor. Unlike an index data type, where the index carriers can vary, the parameters database must always be the same. No, it is not equivalent. You lie. So yeah, in this definition, they can vary. But in this definition, they have to be the same. The forward, the flipped M, they need to be the same. So if you're pattern matching on total to forward, or you're pattern matching on to flipped, the M's remain the same. Unlike an index data type, where types can vary. In a parameter-based database, the parameters must always be the same. Declarations are shorter and easier to read, and occasionally aid act as termination checker. We use them in preference to index types where possible. But to repeat, they're talking about this thing. This thing distributes over here and here. But the alternative way of writing it is to use this and that. But the big difference is that this M will be used here and here, and they have to be the same. But in here, the M only goes to here, and it does not necessarily is the same as this M. So, and it's kind of nice to have that. What I thought was that this would be an existential, but then I thought about it more, and I saw it here. It's like, no, we haven't used existentials at all, so this is not an existential. I don't know what this is. It's per constructor introduction of. This is actually a more powerful definition than, or more powerful syntax than Haskell. I get. Well, if they have extensions as well, then yes, then definitely. I haven't seen extensions, so maybe they use the E. Doesn't anyone know what I'm talking about? I don't know. I know what I'm talking about, so well, I pretend I know what I'm talking about. I say it with enough confidence, and then people believe me. Hopefully. Parameters declarations are shorter, easy to read, and occasionally, with a parameter out of the way, we can specify proof totality. I think my explanation was maybe okay. With the parameter out of the way, we can specify proof totality. Yes, we can, of course. What is this then? Oh, it's repetition, I suppose. It's the width. I don't like this. I already feel I need another break. Okay, let's figure out what these dots are for now. With the parameter out of the way, we can specify proof totality. In the case the proof is by induction over both the first and second arguments, we perform case analysis. First, base case. If the base case argument is 0 and the second argument is n, then the forward case holds. We don't need to read it because the things we understand. I need to go here with the with keyword. Second base case, inductive case. In the first argument, suck m. The forward case of the inductive hypothesis holds. This is the first use of the with clause in Agda. The keyword with is followed by an expression and one or subsequent line. Each line begins with ellipsis and the vertical followed by a pattern to be matched. Every use of with is equivalent to defining a helper function. The following definition is above is equivalent. Well, why didn't you just write it out? Come on. I wonder. Jesus, lame syntax. The first thing I thought when I saw this abomination, how can I rewrite it into something I understand? Because it just doesn't make sense right now to introduce a bunch of syntax I don't get. So let's keep it easy and simple, and we can use the advanced stuff later when we are grown up. But we are not yet, so. Darn, it doesn't work. It is still using where. I don't know what the where does. Oh, wait, the helper is not a scope, so we need to put it above. Right, we need to introduce for all. Is it dot? I don't know, I don't remember. Implicit. Oh, it's just an arrow. I don't know. No, come on. Implicit. I don't know. Didn't work. Ooh. They got us. I don't like with at all. I don't like where either. I want to have it as dumb as possible. How do I make this more dumb? For all. What if we just do no for all definition? On the scope M. So I need to do for all. Forward constructor of database N. Now you're saying the helper doesn't have these things, so we can put them in. There we go. Nice. Yeah, the reason I'm doing this is because Agda is a difficult language, and I'm not gonna maybe A for all. There we go. Cool. Yeah, Agda is a difficult language, and I don't want to I don't want to deal with all of the syntax shenanigans you can do in Agda for now. We can look up what these things mean later, but they're gonna make me read it, don't they? But that's like, you know, okay, at least I understand how to desugar this now. So yeah, if you look at it, like the game is next to nothing. Right? Compiler engineers, they just like introducing syntax or something, I don't know. I like to keep things simple. I'm a simple person, simple ideals. I'm literally from a small village town where things are normal. You're just like, with your with keywords, come on. Just easy stuff, okay? Everybody says, thanks for helping me desugar that. Anyway, this is also our first use of where clause. Yeah. Like, oh, this is how we desugar it. We're using another new thing for you. You cracked me up like that. I think, and the thing I just did, desugar it all the way. They're not even doing it in the book. Especially the keyword where is followed by one or more definitions, which must be indented. Any variables bound on the left hand side. And scope and definition. I thought they would have already introduced where somewhere, because, like, you know, same as in Haskell, I suppose. I just knew that I need to get this from somewhere. That's what I did here. I thought I could make it one expression with total, but no, can't. So I settled for giving it an argument and ignoring it. Yeah, what these M and N do, by the way, is they carry the information of, you need to, how do you explain this? You need to, because it's a dependently typed language, it needs to know what this M is at, not at compiled, well, yeah, at compiled, like, it needs to be the same as the one in the helper. So you need to pass it. But if you pass it like this, it will know which one it is, because there can only be one of it. So yeah, you need to pass it like that. If you don't do that, you will run into trouble. Well, maybe not, because total could figure it out. The problem I have is I don't know how to do the for all thing. Maybe it seems a bit superfluous. Superfluous. Because the M and N are already passed into total, right? So you would say this would also work. No, you don't like that at all. You can split an argument non-data type. Access of type top. No, it doesn't work. I don't know. I think you should be able to do this, but I don't know how. So yeah, because we're not using it, right? And you have the arguments here. I would say, I don't know the syntax. Annoying. Maybe we'll encounter it later. Maybe they will introduce something not as useless as with, and they'll introduce something to deal with that at type level. Maybe use implicits. Maybe you do use implicits. It's worth a try. We're not even giving annotations to these things because it doesn't matter. It's funny. If you have the implicits, you don't need the parameter, right? That's how it works. You pass them. Does this work? Yes! Oh, that's actually sweet. Wow. Look at me. Writing really clean code. And we don't have syntax abomination found. It's not even shorter. That's the thing that bothers me. It's the same size. Why wouldn't you just make a function? You're not saving anything. You're just introducing syntax. I'm upset. Okay. Yeah, so I guess, wait, alright, we were doing the total proof, but that's just because of the, we will explain how it works. So I think we can move on to monotonicity. If one bumps into another operator and the party analogy, I love that. If one bumps into an operator and an ordering at a party, one may ask if the operator is monotonic with regard to ordering. For example, if addition is monotonic with regard to inequality, meaning the proof is straightforward. Using the techniques we have learned, and it's best broken up into 3 parts. First, we deal with a special case of showing addition T is monotonic on the right. Copy paste monad. Proof, but wait, what is monotus? Ah, wait, it's not straightforward at all. And should be short, but it isn't. What? Is it a bug? P U N should be a sort, but it isn't. Is this a joke? My copy paste monad is broken. If one bumps into an operator and ordering at the party, one may ask if the operator is monotonic with regards to that ordering. For example, if addition is monotonic with regards to inequality, meaning for all M and PQ, M is smaller than N, P is smaller than Q, plus P is smaller than. The proof is straightforward using techniques we have learned, and best broken up into 3 parts. First, deal with the special case showing addition is monotonic on the right. So if P is smaller than Q, we can add any N on both sides, and the relation still holds. I forgot to do the fixicity thing. I didn't copy that over. Something, maybe I got bored. I probably got bored. Infix, yeah, that's it. Yeah. sorry. It's to weaken the it's to tell the thing that do the N plus P first and then do the so basically doing this. Yeah. Because I think what I was doing just now is this, which is kind of confusing. Yeah, so we don't need to do that. That's why you should make sure you have a good copy paste monad available at all times. Because if you, well, you could you could get stuck on these kind of errors for a long time if you don't have HD or schizophrenia or both, like some people that are streaming right now maybe do. Yeah, so we proved it. The base case, are we still reading these proofs? Yeah, but like, you know, it's kind of obvious. Yeah, you're just peeling it off. That's kind of cool because we already did the suck thing, right? You're just sucking it in. Upsucking. Second, we deal with this special case showing that addition is monotonic to the left. This should approach this result in commutative of addition. What are we even proving? M is smaller than N. P is smaller than Q. M is smaller than N. P is smaller than Q. M plus P is smaller than N plus Q. So you take the 2 bigger things and you add them together and the relation still holds. Okay, that's what monotonicity is. I never knew. Mono. Mono number 4. Second, we deal with the special case of showing addition is monotonic on the left. This follows from the previous result and a commutative addition. Okay, let's copy paste monad this as well. Oh, they're using that thing. Oof. Okay, let's rewrite the rewrite. I don't think I don't want to deal with this. I actually want to see how difficult it will be to rewrite this. To not be a rewrite. I think it's just dealing with conj a lot. This is basically magic, and I put it in there. It's one of the magics. Like the introduction of syntax is no. it's just a troll you, right? Oh, we introduced the with keyword. Oh, by the way, we explained the with keyword with the where keyword. We also introduced. But this thing. It's just introduced like, oh yeah, we use this thing called rewrite, and good luck. It's like no explanation at all what else. But I asked my internet friends, and they told me that yeah, it's conj. It's like doing stuff to get a conj. But we have the power of proof at our side, so we will prove it with conj. I really don't like rewrites. I think we actually have to do proper proof this time. Because, no, actual inductions. I'm not sure how difficult this will be, so I'm just gonna do the, I'm just gonna do all the formalities. And yeah. We're going to open up the entire arsenal proving. So we are starting with, well actually, what are we starting with? We're starting with what? Oh right, okay, I see. Okay, so we're starting with M and P here. I'm not sure if we can do it like this because we need to end up with begin. Oh no, I have no idea what this thing does then. How annoying. Why does it use rewrite? Okay, maybe we should pay more attention to the book. Rewriting converts M plus P into P plus M, P plus N. What? How does it do that? What? Oh, you're using commutative plus commutative. But how do I do this like in steps and not with lame weird ass syntax that I don't understand? Rewrite. I didn't expect them to use rewrite in examples. Here's this magic piece. Just deal with it. I don't know. Did we have begin? We didn't. Oh, we did get the equality thing. We didn't get a begin keyword or QAD. Maybe we're too maybe that's too dumb. That's for we should use rewrite now, but I don't like it. Yeah. So I'm not sure what it does. It's using this property com, which we import there. That's properties mp com mp. I don't know. At least I did the rewrite here. Can I tell it to unrewrite? So it's rewriting both these properties, com mp and all np, converts m plus p. Maybe we can just p plus m, p plus n, and then I wanna try this. I'm gonna import the step stuff like a plap reasoning, hack reasoning, this thing. Yeah, because I don't wanna. Is it natural also? Induction. What do you use? Yeah, QED. I'm gonna do this. No lame rewrites in my time. I think this is the right way because you shouldn't rely on magic to prove things. The entire point is to get rid of magic. Why would you? I don't like this attitude. So this thing asserts equality between terms, and I was kind of sure we can do this. So I was like, what is equality? What is equality? But what if you just put this entire thing in, right? No, because this goes here. So what are we yielding then? No, we don't want to do that. We want to do it like this. What? This doesn't make any sense to me. This is not a proof. I don't know what I'm doing. Well, the result of our thing should be this, right? M plus P. And what we did before in induction chapter is every time we get that induction Agda, we get this thing out, equality. So we were reasoning with these brackets around equality. So what I'm thinking here is like we need to reason with these brackets around all that. But we don't import that. We're left on our own devices. So that's like we don't have the steps, basically. Step mechanism, I guess. MNP. So how would you get that back? Because what we did before is we just jam this operation into between here, and it would rewrite like you would do. You would transform this proof a little bit, and do the next step. Yada yada yada. But now I don't know because our tools are taken away from us because we are using a different relation now. We're not using strict equality anymore. We're using less than or equal equality, and they're telling us to use rewrite, but I don't want to use rewrite. So But the problem I'm having with rewrite is that I don't know what it does. And that's bad because the idea of proof is that you follow every step along the way, even if they're boring, tedious, annoying. Yeah, you should just write them out. Too much magic. And maybe I'm very pedantic about this, but this is because I'm a beginner and I want to do every step. It's like writing out ASIN definitions when you're a beginner in Haskell. It's very tedious to do, and you probably shouldn't do it. But like you'll learn from doing a couple, like one or two, and then you're just driving ASIN from a 2JSON. And you never look back. But yeah, I wrote those as well, like a little autist. Yeah, so converts m plus p on an m. Maybe yeah, maybe we'll skip like this mark this with to do. Maybe we'll find some magic later on. Because I don't believe that they would expect me always to use rewrite, right? Like they would, maybe they would do. I don't know. I don't know. These people seem cruel. Like for the amount of time they put into spelling every step out, the examples are really like it introduces a lot of crap. Yeah, better combine the previous two results. Okay, so let's just mark this with a comment to figure out how to get rid of rewrite. To figure out how to get rid of rewrite. Because the tools I used before don't work right now. Maybe I'll ask someone as well for this. Because yeah, the book is not helpful. I'm gonna get some water actually. I'm gonna do another water break because yeah, I have some more talking to do, I suppose. Monotonic with regard to inequality. With regard to inequality. You mean it's not inequality, right? Oh, they're calling it inequality. Or less than equality? Less than equality? Inequality. Got some water, yuppie. Be right back. Look at the great backgrounds again. Quick fika break. Be right back. Okay, I am back. Welcome to my stream. Where we panic about rewrite for like 20 minutes and then decide to use it anyway. Because, yeah, like, you know, if you want to do the exercise, it's, what are they doing? Man. So, combine the previous two results, copy paste monad, done, right? Okay, great. I wonder if I can just like kind of play around with this. Like, what if you do this? Oh no. What if you like swap these around? Does it know? Does it care? Is it a god? What is rewrite? Doesn't care. It doesn't care at all. What does this do? What if I make it like cosine? No, it does care about that. Okay. What if I delete one of them? What do you do? Just like this. You don't know. P is not equal to n. Commute m and p. Converts rewriting com mp and com np converts m plus p less than or equal to n plus p into p plus m equal to p plus n. And what you're saying is that we have a rule. Oh, I understand. I think I get this now. I thought about it more. I'm using my big brain. My big brain. My thing that I call the brain sometimes. But you know, we could also call it like an ornament that is very pretty and may sometimes have the decorative electron fire, but we all know it's not really a brain. It's not really. No, it's not at all. Not at all. But I just had a little idea because it says we want to convert blah 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 blah, blah into that. What if we make a function that says you are in fact equal, because we know we can rewrite, so we can factor this out as a real property. What if we do this? And then we can use our previous tool, because now we're no longer using relationship. Bullshit. No. We are using real function. Soy, it works. It has no binding, but it works. So we can just do this and then raffle, right? But actually, like, if you think about it more, we can guess pattern match on it. What do you do? Put in the things. M N P P M P N M N P P M. Yeah. Put in the things. And then M N P, and we can just rewrite. right? Rewrite raffle, done. That worked! So, okay, like you're saying, yuppie, you're not even having any progress right now because you're still using rewrite. But I want to know if I can use this as a function application instead of rewrite. So I like reduce the problem. Yeah, that's what I'm gonna do. I'm gonna get rid of this. So now we have it out of the pattern match here, and we're gonna try apply this to here. I don't know. I'm gonna put in where the function. Put in the function. Yields that we have the assertion there. So there. I don't know. What do you expect? Like that? I don't know. I don't know. It doesn't really work because it's not it's not returning these arguments. It's returning something else. It's returning that equality thing. So yeah. I don't know what. Darn. I thought I was so clever. So I can't even figure out the. This is how little I know about Agda. I can't even figure out how to make this into a function application. Even just like getting the thing out, problematic. K-split solves everything. I have no idea what a K-split is. What? How do you K-split? What's a K-split? The book doesn't tell me either. Yeah. I wanna like make it like I know what I want to do, right? I wanna somehow say apply this function to this thing. So I put in this function, this side, and then I get this side out. I guess. I guess I don't really want an equality here at all. I just want another argument, to be honest. But then this rewrite thing doesn't work anymore. Split. Well, your move. Maybe that's it. Maybe we should just put it in like that and return it because the rewrite did this magic thing. Of course, we all know that worked. What? You're lying. So I guess we need to apply it to mn. X. No, that doesn't work at all. Alright, because you still need to have arguments here. P and M. And P. No, it doesn't work here. P is not of M. Guess I can reverse it. P and M. P is not M. Oh. K-split. Tell me. I don't know. Put in small and Q. Get the thing out. Wait. What? P and P small and Q. Oh, that's probably not a function. Oh no, R. Oh no, you put it in there. Okay. Say so. I don't know. I think I need to probably ask about this because I'll just be stuck on this for a long time. Anyway, so can we do this? Show that multiplication is monotonically required to inequality. I will as soon as I figure out how to get around rewrite. Some more text. Yeah, let's quickly read strict inequality. We can define strict inequalities. Similarly, inequality. The difference at 0 is less than the successor of arbitrary number, but not less than 0. Clearly, strict inequality is not reflexive. However, it is irreflexive. Holds any value of n. Like inequality, strict inequality is transitive. Strict inequality is not total, but satisfies closely related properties of trichotomy. Most of the above are considered exercises below. Irreflexivity requires negation, as does the fact that in every cases of trichotomy is exclusive. So those points are referred to chapter negation. I have a chapter about negation. It's straightforward to show non-negative inequality. Yeah, I'm considering ending the stream here because I just need to ask about the rewrite stuff. And you could say like, hey Yappy, why don't you just play along with the book and do their things? Well, and use the rewrite things, right? I'm just like really concerned if I don't like avoid magic. Like it's too, I think it's too advanced for me to not to use this right now. So I don't want to, and I want to just desugar it because I know this is just like probably getting rid of some boilerplate. So yeah, that's why I'm so obsessive about it. And we got somewhere. Yeah, but I am gonna end it here because I need a break. But thanks everyone for watching, and I'll see you all probably tomorrow, because tomorrow there will be another stream. We're gonna do actual planner game this time. For you know, let a raid. Never get a raid. I had a raid about doing Haskell, and yeah, it was like that. But yeah, tomorrow we're gonna actually do Haskell. So see you all then, and bye bye.